Hi, I am Hake. Today I am going to cover a BCS subject, unit number 6, that is Satellite Communication Link Design. For this unit, I have referred a Pratt book. In this unit, we will see the following points: link equation of satellite communication, noise temperature and G by T ratio, design of downlink, design of uplink, and design of C by N ratio. This is a general block diagram of communication in which left hand side is a transmitter section, right hand side is a receiving section, and in between two we are using a free space. Transmitting side power is known as a transmitted power, that is PT. Receiver side power is known as a received power, that is PR. But in a link equation, we need two more parameters. Those are nothing but a flux density, is also known as a power density, and EIRP, that is effective isotropic radiated power. So let us see the first parameter related to the link equation, that means a flux density, or is also known as a power density. To understand this parameter, let us assume this diagram in which the circle is your isotropic source, and some on a right hand side some surface is there, that is a observer point. Isotropic source radiate a PT power in all direction, that is in all theta and all phi direction. If we measure the power density or flux density at a distance r from the isotropic source, so that power density is denoted by F, or it is also known as a flux density. F is equals to total radiated power by isotropic power Pt divided by 4 pi r square. So in a link equation, we will use a flux density or a power density is equals to Pt divided by 4 pi r square. Second parameter in a link equation is nothing but effective isotropic radiated power, is denoted by EIRP. For this parameter, let us assume a given figure. Transmitter transmit the PT power through the antenna. Antenna is a directional antenna whose gain is a GT. So total power transmitted by a antenna in a given direction is nothing but a effective isotropic radiated power, and that parameter EIRP is equals to PT into the antenna gain, means GT. So last equation is nothing but a EIRP equation. So I think you are familiar with two parameters which we want in a link equation, that is a flux density is also known as a power density, and second is a EIRP. Now let us start a link equation in a communication. Today we will see the general link equation between a transmitter and receiver, and after that we will calculate another formulas related to the satellite communication. Consider a transmitting antenna is a directional antenna. It radiates a power in particular direction. That power is a PT power. Gain of the transmitting antenna is a GT. So effective isotropic power EIRP is nothing but PT into GT. We want to measure the power density across a receiving antenna. That power density across a receiving antenna is denoted by a F, which is equals to PT into GT divided by 4 pi r square. This power density is available at the point of antenna. Now, this formula I can write in another way also. First way is PT into GT divided by 4 pi r square, and second way is EIRP divided by 4 pi r square. Both the things are same. Now, the question comes in a mind, what is a actual power received by receiving antenna? So that power is denoted by PR, which is equals to flux density F into the effective area of antenna, that is A. Flux density is also known as a power density. So in a general we can say power received by a receiving antenna is equals to power density into effective area of antenna. We know power density or flux density in a previous slide, which is nothing but PT into GT divided by 4 pi r square. So here PR is equals to PT into GT into AE divided by 4 pi r square. One more extra parameter is there, that is a AE, effective area of receiving antenna. But effective area of any antenna we can write in different way also, and that is AE is equals to gain of the receiving antenna into the wavelength square, means lambda square, divided by 4 pi. If I add this formula in a previous equation, so my modified equation is nothing but PR is equals to PT into GT into GR into lambda square divided by in bracket 4 pi r bracket square. If we take a lambda in a denominator, then the received power across a receiving antenna, that equation can be modified in a square bracket. So modified equation in a square bracket, a red square bracket is nothing but PR is equals to PT into GT into divided by in bracket 4 pi r divided by lambda bracket square. Here this expression is known as the link equation, where Pt into Gt is nothing but a EIRP, and the denominator part, that is 4 pi r divided by lambda bracket square, is nothing but a path loss. Path loss is denoted by Lp, and which is equals to in bracket 4 pi r divided by lambda bracket square. Now this is a final link equation of a general communication, but we want to see the link equation between a satellite and transmitter, satellite and receiver. So for that purpose we'll use a one downlink. Let us see the final equation of a link equation. Let us consider this figure for our reference. This is a downlink between a satellite and a receiver station, in which the link equation of general communication and this communication system both are same, only the difference is loss. There only one loss is present, that is known as a path loss, but here another losses are present. You can observe carefully satellite. In satellite we are using a one transmitting antenna, so this antenna creates some loss. That loss is known as a LTA, transmitting antenna loss. Then in previous equation we saw the LP is a path loss. That loss will be add. Third loss in any satellite link is nothing but a receiving antenna loss, that is known as a LRA. If we consider a three loss in a link equation, our modified equation is nothing but this equation in terms of a dB. All of you know that in a logarithmic scale multiplication becomes a addition and division becomes a subtraction. So modified link equation with a loss is nothing but PR is equals to EIRP in dB plus gain of the receiving antenna in dB minus path loss in dB minus antenna loss in dB, but there are the two antenna loss, one is the transmitting and one is the receiving, and one more parameter, that is a LA, that is a atmospheric loss. So this is a final link equation between the uplink and downlink. You can see the notation for every loss. So here any examiner can ask the questions related to this theory. Derive the link equation for satellite communication. This is our first question. The second question, obtain the expression of EIRP in terms of flux density or known as a power density. Thank you.